Now, one of the coolest applications of power series is being able to estimate certain calculations, certain expressions, in a way that calculators or computers would do them. If you ever asked yourself how calculators know the answers to certain problems, this is the section of the Calculus 3 course that's going to take you closer to the answer to that question. So let's go ahead and go through it, and hopefully that's going to make sense a little bit more to you. I'll go deeper into this whole how calculators do math at the end of a separate video, but this should be the beginning of understanding this. So the most basic power series that we will see in this course, and really the most important one, the one that supports the development of all other series, is this one. This is the geometric series of ratio r. On one side, you have the sum of these powers of x, 1, x squared, x cubed, and all the way to infinity. And we know that that equals 1 over 1 minus x, as long as x is in this interval between -1 and 1. So that's the starting point of all power series that we're going to study in this video and in the following video that I'll publish soon. So one of the interesting things that you can do here, like I said, is approximating. Let's say I have x equals 1/3, for example. X is 1/3. And if I want to do the right-hand side, that would be 1 over 1 minus 1/3, which would be 1 over 2/3, which would be 3/2. I know this is exactly 1.5, sure, but I'm double checking my math here. It looks fine to me, but if you have 1.5, of course, that's an easy thing to calculate, but you also have the option of plugging in 1/3 here on this side. And do 1/3, 1 plus 1/3 plus 1/3 squared plus 1/3 cubed, and so on. And the more numbers you add on the left side, then the closer you get to the correct answer, which is 1.5. So does that mean that this is an application that I would do? Is that how calculators do this particular approximation, how they approximate 1/3? Not exactly, but for other expressions that we can get from this, then that's how a calculator would do it. So we're going to practice now how we can get new expressions from this basic series. So let's go over the example here, and with some basic algebra, we should be able to, from A, very easily see that 1 over 1 plus x squared is the same as 1 over 1 minus x squared, which, if you go back, is the sum of a geometric series with this in the middle being a ratio. So this in the middle being a ratio. So this equals 1, the sum, and equals 0 to infinity, minus x squared to the power n. So all I've done was replace the ratio with this. I went over the top there, and maybe if I erase this a little bit, I can make a little more clear on this expression at the top. I took this whole thing and replace it in x in here, so it turns into this. So that is the first of many applications, of course, of many expressions you can get, new series you can get. And so of course I can make this look a little bit nicer like this by splitting them up. And this is pretty much an alternating series that you get. And again, you can plug in a bunch of things. You can test this for convergence. And this will have the same interval of convergence. This will have the same interval of convergence as the old one, because the old one converged when the ratio was in the interval. So here, for the interval of convergence, we need negative x squared to be in -1 to 1. So we need negative x squared to be between -1 and 1. So of course negative x squared is always going to be negative, so it's never going to be reaching 1 there. All we need is for it to be greater than -1, like this, and would be good. If we multiply both sides by -1, we'd get that 1 is greater than x squared. So what's the interval that makes this true? For what x values does x squared equal or is less than, excuse me, than 1 only if x is -1 and between -1 and 1 again. So through this calculation, I can get this new interval of convergence. Let me do another one. Let's do example B. Hopefully that's going to make sense. So the next example is this one. Remember, we're working from what we know. We know that's this. And maybe I can even change this x here into an r for the ratio to make it super, super clear. Maybe I don't even need this. We're working from this baseline. So from this, I'm trying to get whatever is on the right side of this and then make this change with the correct value for r. So I'll start with x plus 5. Again, I wish I had this 1 in here, so I'm going to start by multiplying or dividing by 5 this fraction at the top and at the bottom of the fraction to get 1 over 5 times divided by, x over 5 plus 1, like so. This 1/5 at the top I can write outside. And I can also write this as 1 minus x over 5, like so. And then this 1 over 5 I will ignore, but this is exactly what I need with the ratio being negative x over 5. So replace this as the ratio, and then that will become 1 over 5 times the sum n equals 0 to infinity of minus x over 5 to the power n, like so. And then that will be 1 over 5 sum. Again, I'll use a little bit of algebra like I did before to get -1 to the power n, 5 to the power n, and x to the power n, right? And now to get the interval of convergence, let me move this down a bit so I have a little more space to get the interval of convergence. Maybe split this up like so. To get the interval of convergence, again, this equation in black is only true when the ratio is between -1 and 1. So I need this whole thing, negative x over 5, to be between -1 and 1 for that to be correct. So I need negative x over 5 to be like so. I can multiply by 5 in all three sides, and then multiply by -1 in all three sides. Again, multiplying by a -1 switches the sides of the inequality. Again, if you're not really sure about how to handle inequalities with three sides, like three parts, you can look at each piece at a time. Forget the right side for a second, follow through, see if you agree with the conclusions, and then do the same, forget the left side for a second, and just look at this and see if you agree with the steps that are taken in here, okay? So what does that mean? Just x is between -5 and 5, so the interval of convergence is the interval -5 to 5. That's the interval of convergence, right? And that is the power series that we have. So again, taking a step back, if someone ever wants to approximate this for some x value that they don't like, for example, how would you approximate this when the square root of 2 is involved or something, right? It's just a little bit more difficult. You have the option, not saying that this will help, but you have the option of using this power series and just adding a bunch of those terms a little bit. Maybe adding 5 of those terms, 6 of those terms, until you're happy with your approximation. Now x squared. So this is a similar calculation you can make. So this is going to be x squared over x plus 3. So how can I possibly do that? I'm going to split this first into 1 x plus 3 like so. This I'm not going to bother with. It's just x squared. It doesn't make a difference into a series convergence. This is going to be x squared. Again, I'll divide by 3 now to make that 1 appear at the bottom, like so. And then the 1/3, I'll bring out, right? Multiply this x squared by 1/3 gives me x squared over 3. And then this at the bottom I can rewrite as 1 minus x over 3. So x squared over 3. And the sum from 0 to infinity of minus x over 3 to the power n, which then turns into, I'm not managing space very well here, minus 1 to the power n, 3 to the power n, x to the power n. This is not good yet. I was about to box it, but I still have this. So I'm going to take this in. And now that I think about it, maybe I can do the same with the previous one. So let me try and manage my space a little bit better here. Move it up that way. And then I'm going to bring everything into the power series. So this 3 I'll bring in, and this x squared I'll bring in as well. So when I bring in the x squared, I can combine it with this to get an x to the power n plus 2, and I can combine these to get a 3 to the power n plus 1. So if you go back to the definition of a power series, this will be your Cn, right? And this will be your x to the power something. This is sort of shifted. So starts at x squared because when n equals 0. So the first c that you get is not c0. In this case, c0 equals 0, c1 equals 0, and c2 will be whatever value you get by plugging in n equals 0 here. So got to be a little careful with those shifts in your series. But again, if you follow similar calculations as before, because this was the ratio of your power series, your interval will be the interval -3 to 3. And let me go back and do the thing I said with the previous series in bringing this 1/5 in. So I think a more appropriate answer for this would be, in fact, bringing the 5 in. So I think that'd be a more acceptable answer than the previous one that I showed you. I hope this made sense. Next thing we're going to do with power series on a separate video, not this one, will be integrating and differentiating them. So make sure that you get this part before you get to this new integration differentiation video.